Yeah, wow. I'm actually better than my lectures.
Good evening. Yeah, please find your seat. There are plenty of free seats still. Okay. All right. It's my pleasure to welcome you to the third installment of the 4-week series of evenings, Thursday evenings, celebrating the 60th anniversary of CERN. And this week, we have 4 Harvard professors whose work have intersected at CERN, and have a panel discussion about many discoveries that happened at CERN and what awaits us. And so, in place of introduction, I would ask, starting from far end of the panel, I will introduce each. Yes, far end of the panel. I will introduce each professor, and I will ask each professor to tell you about the most memorable visit or stay they had at CERN and what was special about them. Okay, so first off is Professor John Huth.
Okay, my name's John Huth. I'm in the physics department here, and I guess my official title is Donner Professor of Science, and I also work as a venture faculty member at the Radcliffe Institute. So my most memorable moment or moments were around the period of the July 4th seminar, the announcement of the Higgs. I was on sabbatical there and for the winter and spring and summer, and I actually lived in downtown Geneva and commuted back and forth. I was doing a lot of work on analyses, also upgrades to the Atlas experiment, and also in part I was doing a lot of copy editing on a book that I was finishing up and blogging for something called Quantum Diaries. We knew that the 4th of July announcement was coming up, and some of the people who were the publicists for the Quantum Diaries wanted to have us arrange to do some blogs. So the idea was that 2 of the graduate students would go into the seminar on the 4th of July and then sort of live blog and give the updates. And then the next day, the 5th of July, I was supposed to blog and summarize what had happened and put it into context. I guess on July the 3rd, I had a decision to make, which was whether to get in line and stay up all night long to get into the seminar or just go back home to my apartment. And my son was actually doing a summer job in the accelerator division over there. And actually, to be honest, I didn't really feel like staying up all night, even though it meant I might actually miss the seminar, but I could catch it on the internet. That day I went in and I actually looked at the line to get into the auditorium, and it was ghastly, so I just went out to my building where my office was, which is 188, which is way off in the far corner of the campus, and it was just deserted, but I had this quiet little time where I could look at the whole 4th of July proceedings. So I'm sorry, Masahiro, I'll take some time off and other stuff from me. In any case, that went well, and I was happy about that, and the live blogging went well. And then the 5th of July rolled around, and it was time for me to sort of summarize it. Well, wouldn't you know it, but every darn science columnist and their cousin had already taken a whack at it, and what was even worse was they were getting quotations, no offense, from theorists. And the issue was that, you know, it was the accelerator physicists and the experimentalists. I mean, this was our time to shine, right? And so, you know, they were just grabbing all the theorists they knew and interviewing them and quoting them, and it was a little bit disconcerting. So not only were they talking to theorists, but they, and not experimentalists, but I missed the actual thing, and they covered just about every angle that you could. So I was riding in on the tram, trying to figure out what I could write for a blog on the 5th of July, and I was reading this book by Mark Twain called The Innocents Abroad, and as you're probably aware, Mark Twain has a kind of a snarky style about him, and writing a lot, I became hypersensitive to narrative style. So, you know, I would you know, play around with Hemingway and then play around with Twain and this sort of stuff, and it was great fun. And then it struck me that there was a solution to my problem, and I would try to write a blog as if written by a reincarnated Mark Twain. And so I sort of pictured, you know, the previous day, the 4th of July, what I'd done, and I just imagined that you know, the apparition of Mark Twain comes to me from purgatory because he was in the plane of cynics. This is punishment. And then, you know, I try to explain this to him, but if you ever read Innocents Abroad, there's this piece where he's in Palestine and visiting all the Holy Land shrines, and there are all these pilgrims and that stuff. And of course, we call the Higgs the God particle, so there were little jokes that a columnist made about the God particle. So I basically took the idea of Twain and the God particle and pilgrims and just kind of ran with it, and had great fun. And so that may sound a little kind of weird, but it came out, it was entitled The Celebrated God Particle, and it was sort of like everything coming together, the writing and the Higgs discovery and narrative styles, and I don't know, it was just great fun for me. So.
Okay, next up is a rebuttal from the theoretical physicist, Professor Cumrun Vafa.
Okay, so I'm not sure if it's a rebuttal in any way. So my name is Cumrun Vafa. I'm a theorist, and I work on string theory, part of physics which is perhaps as far removed from experiment as you can get in some ways. One of the aims of string theory, probably the most important aim, is to connect to predictions involving particles. So certainly, therefore, connections with CERN is one of the dream goals of string theorists, to somehow be connected in some way to things coming from CERN. So I guess the question was to a memorable, the most memorable connection. Visit CERN. I think I'll give two if it's okay, but two short ones. One is the period where actually I visited CERN for about 1 month, visiting the theory group there. It was, I think, 1996, if I'm not mistaken, and it was a very so first of all, everybody knows about an amazing experiment they are doing there, but they also have a very good theory group there. So I visited the whole group, the group there for a month, and that was a time where string duality has just been discovered, and it was one of the exciting times of theory there, and I enjoyed interacting with theorists as well in CERN. So that is a very pleasant time I had there with my family. We were there for about a month. The other thing I remember from a later visit, when my kids were a bit more grown up, we had a tour for them and myself, in fact, to go and see the actual sites from a theorist viewpoint. This is quite unusual, not like my colleague who sees this every day as a matter of routine, but for me it was quite impressive to go and actually see this equipment. And so you have these huge things, huge magnets and so forth, so you go down quite a number of levels down below the ground, and you see this huge machinery there, and they're all setting it up for the tiny beam width to be passing through this. And as I was watching it, it crossed my mind that there's a huge amount of effort by people, a huge amount of money invested there. Of course, you read about this, but seeing it, it had a different impact on me. And I felt like the things that we do as theorists to predict something or have some predictions, sounds like we are putting much less effort than these guys who are doing all this hard work, this huge machinery just to check these out. I was worried, are we doing our job right? Are we doing enough? Have we tested this? And I felt a bit embarrassed coming from the far end of theory. And I had worked very little up to that point about predictions from string theory for particle physics. And that experience had a transformative effect on me. It resulted in my working on prediction to try to get predictions from string theory, as far removed as it is from experiment, to possibly to have some kind of predictions from string theory to particle physics, spatially accessible at the Large Hadron Collider experiment which was coming up at that point a few years later. So I basically, together with my student Jonathan Heckman, we spent the next 4 or 5 years working furiously, paper after paper, on prediction from string theory, resulting in about 20 papers, trying to see what kind of predictions we can come up with from string theory. So that's one experience I had from CERN I just wanted to share.
Well, Cumrun, you're a little bit too kind to the experimentalists, I'm afraid. May I just ask people to come down and find the seats? It gets tiring after a while standing up there, and there are plenty of seats. Please feel free to come all the way down.
By the way, Mark Twain was disappointed that he got saddled with an experimentalist. Me.
Next person is also a theoretical physicist, theoretical particle physicist, Professor Matt Schwartz.
So I'm also a theorist. I guess we have 8 theory faculty working on the high energy physics of some sort, and Cumrun and I may be on the opposite sides of the spectrum. I'm the most closest to the experiment, and maybe he's the farthest, although despite that small period when he was trying to make predictions from string theory. But I think my story is actually quite similar to his. So my first visit to CERN was, I think, my most memorable, and this was when I was a postdoc, so it was sometime in the mid-2000s. And I went there for a workshop, and the machine wasn't running yet, so it was still being built. And so when it's running, you can't go down and actually see the experiment because it's full of radiation and you'll die immediately. So, but when it's not running, when they're building it, you can see it. And not only can you see it, it's not quite built, so there's actually something to see because they have this cavern where they put these big detectors. And once it's all in there, there's no room for you to stand or see anything. But before it's quite built, it's kind of open up and you can see the parts. And I went to visit both of the big experiments, Atlas, on which John and Melissa and Masahiro work, and also CMS. And I have to admit that I found CMS to be a little bit more impressive. Now, this might have been when it was being built, that when I saw Atlas, it was just these big loops, these what are they called, toroid magnets, and there wasn't much to it. But CMS was the most amazing, it was really one of the most amazing experiences of my life. You go down into this, as Cumrun was saying, into this elevator down 100 meters under the ground, and you walk through some caverns and you go through some safety inspections. And then it opens up, and there's this room, and imagine it's something like this auditorium here. And it's filled with machinery. It's filled with what is essentially a giant microchip. It's maybe a macrochip. It's something that's the size of this room, but every micron of it is a circuit. And it measures all the details of all the particles coming out of these collisions. And it's something as big as this room, but as finely detailed as anything ever constructed. It's one of the most impressive, it's probably the biggest scientific instrument ever made. But to actually see it, it's really awe-inspiring. And it's something that was built, it's 20 years of design and construction. And every little wire and every chip had to be in the right place. They have wires connecting from one part to another, and you have to know how long the wire is because the time it takes for the signal to propagate tells you something about how far the particle went before it hit. They monitor how high it is because it's so heavy it sinks into the ground, and they have to know how far it goes. The beam still hit within the width of a human hair. It's the most impressive, amazing thing that I'd ever seen. And what it did to me is it really had this. It really had the effect, maybe similar to what it did to Cumrun, of changing my philosophy of physics. So before I went there, most of my research was a little bit more formal. It wasn't quite string theory, but I was interested in saying, well, I don't know. We have the standard model, which is what we've seen, and then there's something else maybe. And what you do is you guess what it might be, and then you see if that looks nice. And some things look nicer than other things. And how nice it looks was really the criteria for making something. And with that criteria, there's a lot of subjectivity to it. But seeing this machine, it made me realize that it's not about how nice it is, it's about what it actually does. And if you can't tell the difference between two models, if you can't say this one makes a prediction that one doesn't make, then really you'll never know. And as scientists, we want to know. And so seeing this machine and seeing what we could possibly do made me really want to get as much as we possibly could out of the use of this machine. And it changed my research from being sort of more formal, making stuff up, to being, well, what are the predictions of these things? And from more of the bottom up, what are the actual things that can be measured by this giant machine? So it forced me to go and learn about the details of the experiment and then connect them to the theory. And this really changed my trajectory within theoretical physics.
Okay, so rounding up the panel is an experimental particle physicist, Professor Melissa Franklin.
So actually, I didn't know these two stories of the theorists. This is really an interesting panel. I That's really interesting. Anyhow, I'm going to just talk about 2 times. I'm a little bit older than everyone else on the panel, and my most exciting time at CERN was when I was 19, and I went there for the summer. I had worked at Fermilab, which is an accelerator just outside Chicago, for 2 summers, and I'd met a guy there who was also doing an experiment at CERN, and I asked him, he was doing 2 experiments, I asked him, could I go to CERN for the summer? And he checked it out, and then he said, you can go to CERN if you tell your penguin joke when you get there. It was just a really bad joke. Anyhow, I got to CERN, and the penguin joke is one of those ones where as you're telling it, people are laughing, but when you deliver the final line, nobody laughs. And so I got there, and it was summer, and it was fantastic. The guy, this was a professor from Columbia called Leon Letterman. It was a fantastic summer. I didn't know anybody but theorists. Well, I didn't really know anybody, and I was staying in the hostel, and I knew a few theorists, and they were nice enough to take care of me a little bit. But I remember an amazing moment. So CERN has like a cafeteria, which is pretty good compared to anything at Harvard. And the cafeteria has an outside part, and there are tables and chairs. And I just went and sat with some people that looked familiar. And there was a guy called Sidney Coleman out there sitting at a table, and he was wearing like a polka dot shirt and some pretty big glasses. And he was talking to somebody else. And I just sat with him, and they didn't make me go away. And he was doing a calculation in his head, like a really hard calculation. I knew enough. I'd already gotten through all of undergraduate school to realize what he was doing. And I was just sitting and looking at him thinking, holy shit, this guy's the smartest guy I've ever met in my life. And it turned out later he was. I mean, I didn't know it at the time. But that was kind of a really exciting time. And another that same summer, because I didn't have any friends, and I'm not very good at making friends, on the weekends I had nothing to do, so I just walked. The hostel where you were staying was the same. It was connected to the theory floor. And so I would just walk back and forth, and eventually I would see someone, and I would say hello. And so I saw this old guy, and I said, hi, and he said, who are you? And I said, I'm Franklin, and I said, who are you? He said, I'm Jackson. And so we started talking, and then it turned out it was J.D. Jackson. Now, most of you probably don't know who that is, but I'm Canadian, he's Canadian, and he wrote that book, which if you're a physics student, you know pretty well. Just to finish, my first summer there, I was working for a guy who had 2 experiments, and the other experiment found the bottom quark. I was on an experiment which was colliding protons together, really not finding anything. But it was a kind of exciting time because all the theorists at CERN thought because I was working for this guy, I would know what was happening with the bottom quark discovery. So they took me out all the time. And they tried to get me drunk so I could tell them things about the discovery of the bottom quark. So that was a kind of exciting time for me. I was very young. Of course, I'd never had anything to drink before. Anyhow, that's probably enough.
Thank you. Okay, so speaking of discoveries, discovery of bottom quark was a Fermilab experiment, but CERN is renowned for, right now discovering the Higgs, but there has been many interesting discoveries before that. For example, 1983 discovery of W boson and Z boson happened there using the first collider that actually accelerated antiproton to collide against protons. The idea that was used later very successfully at Fermilab to discover top quark. And there was also a very important discovery of weak neutral current. I think that was in 1973, right? And
if I think about it, many of those weak boson-related discovery has been done at CERN. Now, I would like to ask, again from far end of the table, what makes the latest discovery of Higgs boson special, and what it means to our understanding of physics, and how does it change our perception?
Well, that's a tall order. So the Higgs is a strange creature compared to all of the other particles, and I guess everybody sort of knows that it creates, or people should know that it more or less creates mass for particles. But the problem, I guess the way I would put it, is that when you have these massive cousins of the photon, the W and the Z, you run into problems at very high energies, and it's because of the mass. And so what the Higgs mechanism does is it allows you to have a primordial theory where everything is massless. And then by virtue of the way the Higgs couples to the other particles, it confers a mass in a way that gets rid of these problems, these infinities that plague the physics that we have. And it also ties together in kind of this tight network of what we call vacuum loops. So inside the vacuum in free space, you're always getting particles created and going away all the time. But these vacuum loops have measurable effects you can have. And so once the theory of the Higgs was put together, it looks a little bit weird at first because it's based on a theory of superconductors where our entire universe is permeated by this field. So that's a little bit strange. But what it does is it allows us to make, for the entire standard model, workable predictions, and we were even sensitive indirectly to the mass of the Higgs before we saw it, because it corrected or changed a little bit the mass of the top quark and the mass of the W. And so we had a hint about what the mass might be through these vacuum effects. But then really to see it coming out very close to that predicted mass with the properties was rather astonishing, especially when you consider that I'd been working towards this for 30 years or something like that. So it had a very strong effect on me because it was sort of the culmination of my career as an experimentalist. And I think it ushers in a new era because I guess when I was an undergrad, very famous theorist, Tini Veltman, gave a talk, and he was saying, well, for the next 30 years, theorists are in the driver's seat. And I said, oh, great, that's they can predict everything, and we're just going to measure a few more parameters in their model. But after 30 years, then everything kind of opens up, and there are all these questions. So the discovery, in a sense, validates a standard model, but now there are a whole bunch of mysteries that Veltman was really alluding to, and he said that at that point, experimentalists would be in the driver's seat, and they're really looking to issues that were not quite cleaned up by the Higgs, and that's one of the issues that I think we're making a transition to now at the moment. So.
Thank you. Cumrun?
So the Higgs particle, as John mentioned, was one of the amazing predictions of standard model, which close to 50 years prior to the experiment was predicted. But being predicted is one thing, and seeing it in experiment is quite another. And in fact, over that past few decades, people were trying to revisit the issue of Higgs and the standard model and trying to modify pieces of it for various reasons. There are various fine-tunings which seem to appear in the standard model. Some aspects of it were not very pretty, and so people came up with lots of alternatives to what could be, whether you can have many Higgses or this property or that property. So there are very many ideas. In fact, some ideas were so different, in some suggesting that maybe there's no Higgs particle at all, and there's some kind of a very complicated system of what we call something like a conformal theory, something complicated, replacing even the Higgs particle could be possibly related. So there are many ideas around, despite the fact that the Higgs particle in the context of standard model was suspected or predicted about 50 years ago. So when the Higgs particle was discovered, there was an amazing excitement for, first of all, finding the particle there, the Higgs particle there. So that was the confirmation of the standard model. And a second later, you could begin to think, what if they hadn't discovered it? Would it have been better? And in some sense, it would have been for theorists, it would be far more interesting, perhaps, because you would raise all these possibilities, or perhaps even better for theorists if they had discovered something else, but not Higgs, so that they would be teaching us something which we didn't know about, or something we weren't suspecting. Of course, having said that, they have already taught us a number of things. They have already taught us that many of the alternatives that people had put down for Higgs is incorrect, and that's what science is all about, making concrete, exact predictions, exact experiments which can rule out predictions and validate some particular theory. So that's the way science should work, and that's the way it did work. So at the same time as it was exciting, it was a little bit questioning, okay, so now what do we learn? What are the alternatives? And so there are all these questions that comes up about what next. And so what next and how the physics changed after that is still, I think, not clear to me. That is, certainly there's going to be more accurate measurements and various aspects of physics related to Higgs particle, which people have made some predictions, and so you want to make more what's called precision tests of the standard model in context of Higgs physics. So that's one thing which is going to happen. But people are still hoping that there are pieces of the puzzle which are not contained in the standard model for various theoretical reasons. And so people are still hoping that there might be new signals, new particles, or new things coming up in the context of the experiment that is taking place at the Large Hadron Collider. Whether that will get actually realized or not is unclear, and maybe it won't be clear for a number of years, so we cannot be sure at what point we can say the main discovery is just Higgs or not, but certainly Higgs has been one of the most fantastic results of the past few decades of experiments, I would say, and I think it's credit to the experimenters that have managed to do this, and I think our two colleagues here, experimental colleagues, take a share of that there's such an amazing confirmation of this theory, and the fact that the machine works so beautifully is really remarkable to a theorist's eye, so I'm very impressed with the results.
Matt, your take?
Yeah, the Higgs. So I don't know what to think of the Higgs. On the one hand, I agree with Cumrun that it would have been nicer not to find a Higgs, because then we would have had a whole future of all these different things, and we've had a lifetime of sorting it all out. That's on the one hand. On the other hand, what are we trying to do as theorists? We're trying to come up with a simple description of everything, and you can't get simpler than the Higgs boson. This was kind of the goal of theory, is to write down some really minimal thing that explains everything. And we've done it. I mean, it was done 40 years ago. And we've been trying to make it more complicated ever since, because we don't like things about it. There's aesthetic features of this simplicity that are bothersome, but it is pretty darn simple. So in a sense, it would have been nice not to see it, so we would have stuff to do. But on the other hand, now that we've seen it, we have a kind of a complete model, and we don't really know that, we don't have a guarantee that we'll see something else. We've known for 40 years that we had to either see a Higgs boson or something else, and now we finally discovered it, and it looks like a Higgs boson, it smells like Higgs, but it may not be a Higgs boson. And part of the future of the LHC for the next at least 15 years will be working out the detailed properties of this particle to make sure it looks and smells like a Higgs boson, and we're really hoping to learn something deep. But there's a very real possibility that it may just be a Higgs boson, and we have to reevaluate what are the driving principles behind particle physics? What are the organizing principles? What are we looking for? What makes things nice? What makes things not nice? But we do know that that can't be all there is. It can't be that, okay, there's a Higgs boson, there's a standard model, and physics is done. Because the theory we have is really a mess. I mean, it's just got these pieces here and there, and it's kind of everything's thrown together. And and there's a sense in which the Higgs boson is simple, but there's also a sense in which the standard model is just this incredibly complicated thing. And it's relative. It's not as complicated as other things, and it's not as simple in other ways. But whatever it is, we don't understand it. We don't know how to calculate things to all precision that we want. There's issues of quantum gravity. There's issues of quantum field theory itself. There's just, we don't really know what we're doing. So what we're hoping is that nature will provide us with some clues. Maybe there'll be clues that we thought of, but we've been kind of looking everywhere we've been thinking to look. So now what we've got to do is look other places. And it's hard to look at places that you haven't thought to look. And that's a real challenge. And I think that the experiment is doing a great job trying to just look without biasing the way they're looking. And we're really hoping that nature will give us some clue about physics beyond the Higgs boson. But we have no guarantees. So what's going to happen over the next, I don't know, 15 years at least, is putting things in perspective and reevaluating, what are the guiding principles behind particle physics. And in this sense, the Higgs boson has completely changed things. It put a dead stop to certain kinds of models. There were models like Technicolor that until 2011 were viable extensions of the standard model, and then the discovery of the Higgs boson said they're all wrong. So it really put in the trash bin many different alternatives to the standard model. Of course, there's many still there. Supersymmetry is a prominent one that hasn't been ruled out yet, and we're still hoping that there's a hint about supersymmetry as a guiding principle of nature, but we don't know yet. So I think it really has revolutionized particle physics in very deep ways, and we don't know from either a practical point of view or a philosophical point of view how to think about that. And I think that'll come out as time goes on, but we don't know yet.
It's very comforting here from theorist's mouth that we don't know what we're doing. Okay, Melissa, your take.
So I should just, we're having a love fest here, so I should reciprocate. The theorists are amazing. I'm amazed that they can go into their offices every day with incredible energy and thought and just dream stuff up, which probably isn't right. And they just keep doing it. It's fantastic. And like every once in a while, 1 out of like 2,000 of these papers is right. Like this. And isn't that wonderful that we have people to do that, brilliant people to do that? I think that's one of the greatest things. So I personally think the theory is incredibly beautiful, but I have lower standards. My standards are pretty low. I just also wanted to say to Matt that we don't actually measure the smell. We're working on it.
Can I also add, it's really amazing that these experiments are willing to work for so long when they may not discover anything at all.
Oh. Yeah. No, I was actually trying to be nice.
Let's give it.
So I have a little bit, when Masahiro asked this question, he sent us an email, this question, I had a kind of different take on it. So I sort of meant, the question was like, personally, what does it mean to me to discover the Higgs? So I'm fascinated by the question of what is the universe with nothing in it? Like if you take everything out, like all of you guys and the Science Center and everything else and all of the atoms, what's there? That's kind of a really interesting question. It's sort of like a Samuel Beckett kind of question. And this question of the Higgs field and filling the vacuum of the universe is just mind-bending to me. So now, like when I'm walking down the street or through Harvard Square, I feel it. I feel different. So like on July 4th, the difference was I was now feeling a little weird. And it turns out that the theorists have been feeling weird for a while. Because when we discovered the W and Z bosons, so that's sort of, those bosons having big masses was sort of meant that there had to be something like the Higgs. So it turns out that my friends, the theorists, were feeling a little prickly, just a little bit funny, but I just started recently because as an experimentalist, I just didn't believe it. So there's that, and the other thing is that for years and years and years, since Higgs and the others, Englert, we've seen this picture of a Mexican hat, and the Mexican hat is a picture of the Higgs field, the potential, and it's a really nice hat, but nobody knows the measurements of the hat, like how big is the head part and the brim. And so I feel like we now have a chance to actually measure the size of that hat. Do you know what a Mexican hat? Yeah. Yeah. A sombrero. Yeah.
There's a blackboard behind you if you want.
Yeah, so, I don't, luckily there's no chalk.
Oh, really?
And now imagine a rotation. So the point is, it would really be nice to know, how big it is. And that would pretty much describe our entire universe with nothing in it. So I'm really excited about measuring the hat, and I just hope I can measure it before I die. That's a bit different.
Okay, now that the audience is sufficiently warmed up, I would like to get some questions from the audience. However, let me first pick on our students because I need somebody to carry the microphones, and there are some students of John and Melissa hiding there. Can you guys just raise your hands so that people can see that you are Atlas students? Oh, good. All right. How about okay? Steve is most accessible. Next is what? Who? Julia?
Yeah.
Okay, Steve and Julia. Can you help?
Earning my paycheck.
Okay, first question, right in the middle. Yeah. So,
Stand up. Simple question, Melissa. What experiments could help reveal the parameters, the size, to measure the Mexican hat? What experiments?
Well, I mean, I think the collider, the LHC can go pretty far in measuring part of that slope, part of the, the depth, et cetera, and the slope. Are there more? Maybe Matt knows if there are better experiments.
yeah, Matt, can you fill in?
Sure. Well, I think that they've already measured it. So there's the overall offset, how high it is, which maybe is
That's
not
the
part of
only
the hat.
That's the only thing they've measured, right?
Well, that's the cosmological
Yeah,
constant.
yeah.
That we know since 1998. And then there's the curvature around the minimum, and that's what you guys measured. That's
Yeah.
the Higgs mass.
Yeah.
And then there's the height, which you actually knew since 1930 from the Fermi constant. So actually, we know everything.
No, you don't know everything.
Well, within the standard model, we do.
Really?
Yeah.
You know, how big is the hat
Well-
then, Matt?
In what units?
H bar C?
6?
It's a 6?
It's a size 6 hat.
Oh, wow.
Well,
That's wild. Who said that? Who said that? Thank you. Thank you so much.
Thank you.
More fairly, there's three parameters that determine the hat. The quadratic term, the curvature around the bottom, and then there's a cubic term and then a quartic term. And we haven't actually directly measured this cubic and quartic term. So that's something that the LHC would love to measure. It'll be very, very challenging. But with an upgrade, it's possible to maybe measure that cubic term, which would be a very, very important consistency check that it is the Higgs boson. And if you see a deviation, if it's not consistent with the things we know about it from the Fermi constant and the Higgs mass, then it would imply very deep missing ingredient in our understanding of nature.
So did we measure the hat?
Yes, we measured the hat.
And the cubic term and quartic term, experimentally, what does that mean? What do we measure?
Is this
what-
an orals question?
Yeah.
This was an orals question in one of the oral exams. Yeah, actually, you want to see the Higgs couples to the Higgs. That's kind of what it means, and the strength with which the Higgs couples to the Higgs, because although this is part of the theory that's cast in stone at some level, there can be other interactions out there that could alter what we think of as the Mexican hat potential. So there could be higher order terms that are in there. And because it's so intimately coupled with this question of vacuum energy that Melissa spoke to, it's very important that we test how the Higgs couples to itself. So you have a Higgs and then it decays into a pair of Higgses. And to get there, you have to have a huge amount of beam time at very high luminosities, which is basically the amount of protons that you're scattering. And to do that, we have to have very ambitious upgrades of the experiments, and also there's a fairly ambitious upgrade to the accelerator that has to be done to be able to deliver that kind of luminosity. So, so I would say it's pretty important.
Yeah, we still prefer to get more beams than waiting for 100 years. Especially the students. Next question. Ooh, nobody has a question.
My question is whether or not this Higgs mechanism works to actually provide mass for dark matter, or is that something as a separately not understood category?
Who would like to take that question?
Well, we're going to look to see if it does.
In the standard model, no, there's no dark matter in the standard model as far as we're aware, which is, I mean, we're talking about a huge fraction of the universe, which isn't made of quarks and electrons and leptons and that sort of thing. So right now, now there are variants on the Higgs, which is the interesting question in this model called supersymmetry, where you might get something that looks like the Higgs that we found, but there may be other Higgses, and those would be associated with dark matter terms. And so, in fact, that's one of the reasons why you just don't stop and give up, because there may be other Higgses out there that have slightly different properties, and right now we're eyeing some of those in the early running that starts up next year.
So actually, perhaps I can comment that this question also points to the fact that the popular label God particle is a bad terminology, because if it was a God particle, it gives mass to everything, not just to the things that we see, also the dark matter. So that's a bad terminology.
Can I add, it actually doesn't give mass to much at all. So most of the mass in the universe, so what is the energy in the universe is mostly dark energy, and then there's some dark matter, and then there's some matter. But the matter is mostly protons and nuclei, and they don't get mass from the Higgs boson at all. They would have mass even if there weren't a Higgs boson. They get mass from some other mechanism that's been understood for a while also. And so, in fact, the electron gets mass from the Higgs mechanism, but that's about it. But not much of the mass of the universe is made out of electrons. So it's really misleading to say that it generates mass for the universe. It generates,
So,
it's
you're
a
so
mechanism.
depressing.
But you have to say something, right?
I think it's a really good question. I think we should look for Higgs going to dark matter, dark matter. It's kind of hard, because it's just Higgs going to nothing. What?
No, it's going to something, it's just something we can't see.
Sorry. Higgs going to nothing we can see. I apologize.
Well, we will still look for invisible Higgs decays.
Yes, that's
in
what I'm trying to
tagged
say.
channels, yes. Right.
It's just a little harder.
Okay. They're up there. There's a hand with a pencil.
Assuming that you've all seen Particle Fever, I'm hoping that you might have something to say, either a critique of the framing of this, of the problems, or a resonance with the film in some way.
How many have seen it?
I haven't seen it.
Raise your hand if you've seen it on the panel.
I saw half of it.
I've seen it. I think it's a great movie. I think it does a great job portraying the human aspect of the search for the Higgs boson, both on the theoretical and experimental side. I thought it was very well done. But how about scientifically? Well, they took some liberties, as you must to tell a compelling narrative. So probably from the theory side, the part that's maybe not that accurate is the dichotomy between the landscape as one possibility and supersymmetry as another, and that it was one or the other, and the LHC was going to decide depending on the Higgs mass. I mean, that's not really accurate. There are connections between the mass of the Higgs boson, and it certainly has implications for the possible extensions of the standard model. And a lighter Higgs mass is more favorable to supersymmetry, and a heavier one is less favorable. But since they discovered it, it's not unfavorable, and supersymmetry can certainly allow for quite a large range of Higgs masses. So it's not quite as simple as they put it off. But as a representation of the fact that measuring this does rule out some theories and confirm or suggest other ones, that is absolutely true. So it's true broadly, but not in detail.
Cumrun, do you have something to add?
I haven't seen it.
You haven't seen the movie.
Neither have I. It's one of these things where when you've done something, you don't necessarily read the book about it. But I don't know. I am looking forward to seeing it though, and I've been told it's good.
And I think it's streaming on Netflix.
Is that right? Okay, I'll make a point. No excuses.
No excuses. That's right.
No,
You should have given us
excuses
the
now.
homework, Masahiro. You must watch
so,
Particles.
so we will ask all the students to report at the next group meeting about this. Okay, other question? Yes?
So the theorists talked about how the experiment helps you rule out theories that don't make sense anymore. But I don't understand how the experimenters decide how to design the machines to look in the first place if there's so many different conflicting theories out there around. Because I presume you have to have some set of theories that help you design the machine in the first place.
Marissa?
Yeah, so there's two kinds of experimentalists. They're called good pigs and bad pigs. Some experimentalists try to not think about the theorists and what they're saying at all, and try and be completely unbiased by theory. And then the good pigs are reading a lot about the theory and trying to make sure that we measure, we see if these new theories are correct. So I think it's a good balance, the good pig, bad pig thing. So there's sort of, our experiments are general purpose. The protons collide, and we try and look at every kind of interaction that happens. We also try and concentrate on those interactions, for instance, that might make a Higgs particle. And so it's a balance between those two things, I think, that allows us to do a good job. But it is important to have the bad pigs. You may wonder why I'm calling them pigs. There's a famous physicist, theorist, called Howard Georgi, who believes that, who wrote in the 70s that the relationship between theorists and experimentalists were like the relationship between truffle farmers and truffle pigs, where the truffle farmer finds sort of the right field, and then the truffle pig puts their nose in the ground and finds the truffles. And he thought that was a good way to think about about the relationship. And so for years I felt like a very bad pig. I wanted to be a bad pig. More recently with therapy, I've become a good pig.
Okay.
Let me just,
Yeah, please.
yeah, I'd like to add something to that. So the bad pigs are very important, especially now. So to a first approximation, all the beyond the standard model models show up in the same way. They show up in more high energy stuff that looks similar to standard model, but you get more of it, and they have peaks where there's new particles. So to a first approximation, the stuff they're looking for at the LHC is the same stuff they've always looked for, which is resonances and new particles, and there's a very standard way to look for that. And that's the 90% of the searches of the LHC are of this standard type, because it's a universal signature. So once you see something, then the details of what the angular distribution is and the precise energy can distinguish between different models. But to a first approximation, they all predict roughly similar things. That's one component. Another component is there's only certain things they can measure. So they go out and measure as many things as they can that might hold keys to beyond the standard model of physics. So there's certain signatures. So what you try to do is look for things that are very different from the standard model. So for example, if all the particles go off in one direction and nothing goes off in the other direction, this is hard to do when you know where all the particles are. So it can only happen if you didn't measure the things that were going off there. But you've designed your experiment to measure everything, so it has to be something you can't measure. So they look for that. And there's a lot of searches, and the vast majority of searches for supersymmetry of that type. They look for what's called missing energy. But there's the very real possibility that new physics might be there and we don't see it because we're not looking for it. Because we don't trigger on it, meaning we don't even record those events on our disk drive. We just throw them out because there's a billion collisions a second and you can't save them all. You can only save, maybe 1,000. So you have to somehow throw out 1 billion minus 1,000, and that's a lot. So you have to decide which to throw out, and you might be throwing out the truffles with the pig. So to avoid that, you need to have some good ideas. So you can either go from the theory point of view, make predictions, or you can go from the point of view of what can they actually measure. So you can start thinking about things they might measure that could conceivably come from a theory, even if you don't yet know what the theory is. And I think over the last 5 years or so, there's been a tremendous push to do that, to make sure you're not throwing out stuff. And so far they haven't found anything, but maybe it's just we're not looking in the right place. And that's an important direction in both experimental and theoretical physics.
There's a question about that.
Yeah, you're saying that the Higgs field gives mass to the electron. So what would there be of the electron if there were no Higgs field?
It would have mass, it would be massless.
Yeah, it'd be massless.
Yeah, well, neutrinos are supposedly actually have some mass too, but
Yeah, and actually it wouldn't really be massless. It would get a small mass from other things. So it would be lighter, but not, it would be lighter. Sorry, that's the truth.
But the whole structure of the W and the Z is highly dependent on it, and so the universe would be incredibly different if it weren't for the Higgs interactions. So I mean, it does have, a substantial role, and the electron's the lightest particle, and then you get a heavier particle like the muon and the bottom quark, and these things, and because they have stronger coupling, the world would look extremely different. Especially the development of the very early universe would look very different as a result.
Okay. I would like to see some question from the younger audience.
Younger?
The undergrads, maybe? Yeah.
It's not very, wait.
Yeah, wait for microphone so that the people behind you can hear.
It's really not a good question. We're dying to hear the penguin joke.
No, sorry. It's been years. That was 1977. I've never told it again. But thank you for asking.
Okay, I see one right there.
So I was wondering what the experiments at CERN might potentially tell us about string theory. If we, even with all of these upgrades, would expect to get any direct evidence for or against it, or if we're just expecting to get some evidence that might lean us towards or against it.
So one of the questions about what is beyond the standard model is raised by the fact that the standard model, as Matt alluded to, is not very natural in some ways. So there are some fine tunings and there are some things not very natural about it. So we expect there to be something beyond the standard model, and the question is what is beyond it? What completes the theory? We know the theory as it stands cannot be exactly just it. We expect, at least on theoretical grounds, we expect other things to be there. So the question is, what is there? And so the people have come up with various ideas, and prominent among them, I would say, is perhaps the idea of supersymmetry, to try to say what is beyond the standard model. Supersymmetry is a symmetry which predicts that for every particle there is a shadow particle which looks exactly like the other particle, except it has a different spin. And that was if supersymmetry is a true symmetry of nature. And since we know that's not, we haven't discovered a shadow electron, let's say, we know it's not exactly a symmetry, so it could be a symmetry which is broken somewhat. And the question is how badly it's broken. String theory, in some abstract sense, predicts that there's supersymmetry. At least it's in the most conventional view of string theory, we believe supersymmetry is part of nature. But what we cannot know in string theory is how badly it's broken. So given the fact that quite independently of string theories, people who are trying to describe particle phenomenology beyond the standard model to try to answer some of the riddles or puzzles regarding the standard model had used supersymmetry to describe properties of the standard particles, and in particular why their mass is so low. They were using ideas related to supersymmetry, so this actually could potentially fit nicely with string theory. In other words, if the supersymmetry breaking is such that it's not so badly broken, that means if the masses of these shadow particles is not so far up, that is beyond the experimental reach of the Large Hadron Collider, then we could potentially see some signs of it. So supersymmetry would be an avenue to try to connect particle physics to string theory, and it would be very, very satisfying if that's the case. Having said that, I should say that it's not a prediction of string theory that it will have to be seen at the Large Hadron Collider, because we don't know how badly supersymmetry is broken. So in other words, it might be a smoking gun for string theory if supersymmetry is discovered. It won't be a proof of string theory. And even if it's not discovered, it doesn't rule out string theory either. So I would say the relation between supersymmetry and string theory is like this. There are more exotic possibilities like extra dimensions and this and that, which seems, in my opinion, a bit far-fetched in the context of the energies that are being probed at the Large Hadron Collider. So that, I think, is not the most natural path probably to connect with string theory at this point. But who knows? I think the evidence for supersymmetry is not there yet. And in fact, if anything, things are being pushed to the corner. So you would say supersymmetry has harder and harder time to be accommodated in the experiments in the results of the experiments we're getting. So if you were to bet about supersymmetry being visible at the Large Hadron Collider, it probably would be you would probably better chance to bet against the supersymmetry in Large Hadron Collider. So it's not clear, but it's very possible also that something completely different is seen. So we are expecting that the standard model as it stands is not nice in features, and maybe the solution is not supersymmetry either. Maybe there's something else. So I think that, and if that something else comes, and if that something else somehow naturally fits with some model we understand in string theory, let's say, then it will be renewed interest in those models. So until we find more, and we should look forward to results from our experimental colleagues to guide us in that direction, until there's some hints, then I cannot say whether or not it will be a hint for string theory or not. It's hard to prove or disprove it by the experiment, but it could give some motivation in certain directions of string theory, I would say.
Cumrun, would you expand a little bit on why standard model and that's it is not acceptable?
Well, there are many reasons. Probably the most prominent one is the fact that, there are various theoretical reasons, and there are more concrete reasons. Theoretical reasons is that we already know that the strengths of these couplings that we know about, there are three forces that are at play: the strong force, weak force, and electromagnetic force, which are being studied in the context of Large Hadron Collider. And they have strengths. And these strengths are different when they are measured at the Large Hadron Collider. But theoretically, we know that if you measure them at higher and higher energies, the strengths of these interactions become closer and closer and closer together until it gets to some very, very high energies, some huge magnitude of the order of 10 to the 10 times more energies if you go. You come to energies in which these interactions have exactly the same strength, essentially exactly the same strength. And theoretically, this suggests that these forces are actually one force. They unify into one force. So theoretically, this is, I think, the strongest reason we think there's something beyond the standard model. In fact, Howard Georgi, our colleague, who's not in this panel, unfortunately, who is one of the main proponents of this idea of unification of these forces, which is actually, I think, a very viable theoretical idea. And we have, for example, it predicts the protons will decay, and people are making searches for these things. So it's potentially the right kind of a connection with the beyond the standard model ideas. So that's one idea we expect there to be something beyond the standard model. There are other ideas having to do with the fact that there's what is called the naturalness, or the issue of hierarchy. You might think that the Large Hadron Collider is probing a huge energy. As it turns out, that huge energy just displays our technical abilities or technological abilities. From a theoretical viewpoint, that's a very low energy. And in fact, one of the biggest puzzles about the Higgs mass and so forth is why is the mass so low? Why are the energies that are being relevant so low compared to fundamental scales of energies in physics? So in some sense, that's the main puzzle that we don't think theoretically standard model is complete. What's called the hierarchy problem, the fact that the masses involved in the context of particles that we know, the masses of the electron and the quarks and all that, is so much smaller than the fundamental scale in physics by a huge order of magnitude, 10 to the 15 or whatnot. So there's a huge amount of scale difference. And so we expect there to be some other explanation of why these are small. And you might say, well, somebody tuned it to be small. But the problem is that even if you did that, quantum fluctuations push that knob back all the way up to the big value until you find a good way for this quantum fluctuation to exactly cancel. So that sounds a bit bizarre. So for various theoretical reasons, we think there are things beyond the standard model. We are not satisfied with the standard model, and that is good for theorists.
Okay, other questions? I would like to get somebody from the closest to the back. Is there anybody who would like to? Okay, over there.
Somebody up there.
This is a question about how different fields fit together. I think, John, you mentioned superconductivity in the context of the Higgs experiments.
Yes.
And we've been talking about different energy scales. Well, superconductivity would seem to be at the exact lower end of the energy scales. So my question is, what is the relationship between superconductivity and the Higgs?
Well, let's see. So this is actually to the heart of the Higgs mechanism in some respects. So there was this model of superconductivity. So the idea behind superconductivity is that normally electrons flow through resistors and metals more or less individually, okay? And then and you get finite resistance. But when you cool them down enough, what happens is that they start to act like one big wave function, that they're all connected to each other quantum mechanically. And so at that point, the resistance goes to zero. And so there was this model called the Landau-Ginzburg model, which was a precursor to our modern model of superconductivity. And in it, there was something called the order parameter, which basically is, in a sense, like this pervasive field that Melissa talked about. And what happens is if you take a photon and stick it into a superconductor, it acts like it's all of a sudden got mass. And this is just a basic fundamental property. You can take a physical superconductor and try to put a photon in it, and it acquires a mass. And so the problem that was floating around at the time was we knew that these gauge bosons, these W's and Z's, had mass, but it created all of these problems for the theory to have consistent theory. So the idea is that if you could give them zero mass, everything would work out, and then there was an interaction that was switched on. And so Phil Anderson, who was a condensed matter theorist, suggested that this could be the solution to the Higgs problem, and then this is what then Higgs and Engberg, decided to put together. So they actually took in toto this Landau-Ginzburg model and adapted it with special relativity to come up with the Higgs model. So that was the relationship between the two.
Yeah.
I have two questions. First is, does the Higgs also give mass to antimatter? Second is, I heard different answers. Second question is, does antimatter has positive or negative mass?
Well, it has. So when we talk about quarks and matter, generally we actually include antimatter in that as well. And so it's kind of a shorthand. Antimatter came up when you marry quantum mechanics with at least electrodynamics and special relativity. And when you put them all together, it's a prediction of our quantum field theory. So in that respect, it has to have identical masses so it's a particle that has an identical mass to antiparticle and particle have identical masses, and they have the same spins, but they have opposite charges, basically. And that's basically a fundamental theorem of quantum field theory. So
So the short answer is yes, it's antimatter gets mass from the Higgs interaction, and the mass is positive.
Ah, now you hit on a really good point. Okay, so when we talk about mass, there are two kinds of masses. Ah, I was waiting for somebody to ask this. So there's something called inertial mass, which is an object's resistance to acceleration. And there's gravitational mass, which is the strength of attraction between two massive objects due to the gravitational field. All of the mass that we've been talking to up to this point is just the inertial mass. Okay? And so then the interesting question becomes, well, if there's this equivalence principle between inertial and gravitational mass, and we have this mechanism that makes inertial mass, it doesn't tell us anything about gravitational mass. So, you know, in the back of this person's mind, you keep wondering, you know, is there some connection? There's no theory that really connects the two that I'm aware of, but yeah, he's saying, you know.
No, Einstein's theory. Einstein's made this fame by saying that they're equal as a principle of physics, basically.
Yeah, so that's one of the interesting mysteries is up till now the Higgs mechanism is all inertial mass and no gravitational mass, but you know we know that.
Yeah.
Yeah.
Yes, I think I would say that if Einstein's equivalence principle is correct, which we believe it is, then this already shows that no matter what mass you get from one thing is equal to the other one. So there's no two different ones.
But there's no gravity in the theory.
Yeah, even so.
Yeah.
Equivalence principle. So.
Okay. Okay, other more questions? Way back there.
Hi, I just had a question. I did my undergrad at Princeton, but then I'm finishing my PhD at the École Normale Supérieure in Paris, where they won the Nobel laureate in 2012. Do you think there's anything we can do with the quantum optics experiments in terms of trapping atoms or sending them through a trap that can help us with the things happening in CERN?
Yeah. I mean, there's an experiment here by my colleagues here on the electric dipole moment of the electron, for instance, that could find something which is relevant to what we're doing at CERN, even though it's at a much lower energy. It could find signs for possibly supersymmetry. We wouldn't know it was supersymmetry, but we would know it was something weird, and we would go, wow. And it would be connected. Is that? So yes, I think there are experiments that happen in traps.
Okay, yeah.
Although the collider's kind of a trap. But okay, yeah, it happened in traps that could be relevant.
I mean, I could add so anti-hydrogen, for example, is something that they produce at CERN. So CERN does other things besides collide particles. They're, you know, a great way of making antimatter. And so people will make antihydrogen, and then you have to trap it. So otherwise, if it hits a hydrogen, it'll blow up. So you got to trap it, and then you try to study it. You try to, for example, its spectrum, and you want to see if the photons that are emitted between the energy levels of antihydrogen are the same as with hydrogen. And that's an important test that if they're different, it means that's a deep insight into nature and something's wrong with the standard model and so on. So these other experiments they do at CERN and, you know, testing the nature of antimatter are important, you know, precision and indirect tests that also probe the standard model that are complementary to what they do at the collider in many ways.
Actually, that's something that came up earlier, is this difference between indirect and direct tests of something. So experimentalists love direct. We want to make the Higgs boson. We don't want to just infer it. Theorists like both. Theorists like both, I would say, just like the Mexican hat. So we want to measure directly everything that we can. And a lot of these trapping experiments would infer new physics rather than directly measure.
Okay, thanks. Can I just ask one other thing? Is there anybody leaning more towards multiverses out of the four of you, or are you more all towards supersymmetry, or?
See somebody watch particle theory.
Is it the one or the other question, really? So let's see.
you want to
Maybe you comment. So the questions are related to fine tunings, I think. So I alluded to the fact that what we think about the standard model of particle physics involves a lot of fine-tuned parameter. And the question is, who fine-tuned it for us? And one idea is supersymmetry. I was explaining some ideas related to supersymmetry might explain why some of these parameters are small and so on. Another parameter has to do with, if the parameters were different, then we would not exist as we do, and therefore life is not good. So this is kind of not quite related to this principle called the anthropic principle, that if the parameters were very different from what we have seen, then we would not have existed, or not just us, but the whole galaxies would not have formed, no life would have existed, therefore nobody would have raised the question, and that's the multiverse question. So the question is, which fine-tuning do I like most, multiverse or supersymmetry, or whether we can talk about this. I think the idea is a bit premature right now in terms of answering such questions. Clearly it's not, clearly we're not happy with the standard model as a final theory of nature. It's a stepping stone really, and we are happy with it as a stepping stone. We know we're looking for a better idea of how it works in terms of these fine-tuned parameters. We do not know ultimately what's the reasoning for these fine-tuned parameters. Dark energy, which has now been experimentally verified, is an amazingly fine-tuned parameter, it seems. What's the explanation of that, and so forth? So we don't know yet, and so it's a bit half philosophical in some sense, but I think at this point it's premature to go one way or the other. We just have to learn more.
I just want to add something that I think Cumrun is being a little modest in the sense that if we just measure the Higgs boson and we see this fine-tuning, and we measure the cosmological constant and we see the fine-tuning, then maybe it is evidence that there has to be some kind of selection that says, well, if the Higgs boson were slightly heavier or the cosmological constant were larger, we couldn't exist in our universe. But the only way that you can have a physical model that allows for this is if you have many different universes with many different values of these parameters. So one wonderful thing that string theory does for us is it provides us with a way to realize these different universes, to kind of scan over these different Higgs masses and cosmological constants. So perhaps if we don't see any evidence of anything else, it'll be the best proof yet of string theory is correct.
I just want to answer directly your question. I'm a big fan of the writer Philip K. Dick, and so I think multiverse is definitely what I would bet on. Maybe neither of you would say, okay.
What?
I'm sorry, just because it's like it's not 140 and it's not 115, it's right in the middle. So I wanted to know if there's one of you that's more towards one. Because I went to Princeton and Nemo is at Princeton, Nemo is at Princeton, and Nemo at the Advanced Institute is so to the multiverses. I wanted to know where you stood on it as person.
Nima is very good at simplifying the story, but
I mean, it's a cool idea, but I just don't know. I mean, one of the problems is that you're sort of talking about this inaccessible territory. I mean, there may be predictions, but if you actually talk about a physical universe that you could jump over into, in some sense, it's hidden from our view at the moment.
Multiverse, I think, is somehow related to what Matt was answering. It's in the absence of any better explanation, you will resort back to that explanation. So, as a theorist, I would say it's a negative scenario in the sense that if I don't have a better idea, I will resort to that. Of course, as Matt explained, we are lucky that in string theory we have this possibility to resort back to thanks to the many solutions that we can get to string theory. But as a string theorist, I'm not happy to resort back to that unless I have to. I would say that that's a fallback scenario if we don't have any better idea.
Sort of like saying the universe is like it is because we're here. It's a little bit of a dodge.
It's a little defeatist, I would say.
And I should also add, we're scientists, so what you believe doesn't really come into it. What you want to do is measure and find out the answer, and you want to do the best you can to determining and getting as much data as you can, and that's our priority. And there's the philosophical aspect, but it's important to not philosophize too much and actually do science and try to find out. So It's good for making movies, but in practice, we want to know, and we want to make measurements,
Answers the
and we want
previous
to
question, right?
come up with testable theories.
Okay, how about the left, this side? Okay, yeah, sure.
So far on LHC, is there like any, even if small, hints on significance level, like 2 or 3 sigma, about some new physics?
Mm-hmm.
Yeah.
Yeah.
We can't tell you.
No, there's definite, I mean, in fact, it would be really unlikely if there weren't little hints at the level of 2 sigma, because you can ask, if you look in 300 places, how often should you see something of significance 2 sigma? It's often. So, yes, and all our graduate students get very excited.
Well, one of the things you do when you start to see like a 2 or 3 sigma effect is you make it a high priority for the next run, to go after it and, try to get more statistics. So.
Can you say more certainly what kind of effects there is on this significance level?
Nope.
Like some new particles or?
We can only talk about things that have been published.
We have a secret list of 3 sigmas.
You can look us up later, but not in a public forum in any case.
I think there was a question there.
So I guess the Higgs mechanism was predicted about half a century ago, and we're just now finding it. So as undergraduates, what is the thing that you think that our careers will be built out of, that we will be looking for, and like what sorts of things do you hope that we find within our careers?
That's a
Dark
great
matter.
question. That was brief. Can you say a little more about it?
Dark matter. Dark matter.
Okay.
You guys have to find dark matter, and you better start now. Yeah.
How about you, Matt?
I don't know. I don't know what advice to give. I don't know where things will show up. I think we just have to keep looking, and I don't know.
Well,
Cumrun.
I think it's hard to say exactly what will show up. As Melissa said, dark matter is already believed to exist, and therefore we have experimental evidence for it. Therefore, it's certainly good to understand more about it. So that's certainly a safe bet in a sense. Whether it's directly measurable or not is not clear, but we hope that it might be. I think as a theorist, again, I think one of the important things is this idea I was just mentioning before, the grand unification of all forces, which is already evidenced by the fact that the neutrino, so there's an evidence for it, indirect, well, essentially I would say direct, but depends on how you count the word direct. They have measured the neutrino mass, or mass splittings between the neutrinos, and the mass splitting of the neutrinos hint at an energy scale which is very close to the energy scale in which the forces are supposed to unify. That's already a smoking gun of the fact that this idea might be correct, that there is something going on at that scale, physical new scale. So you could say in some sense, a new energy scale has been measured thanks to the measurement of the neutrino mass splittings. And this points to that direction. So whether it be finding it through proton decay, we might discover the unification of forces or other means, I don't know. But I think the finding unification of forces, evidence for it, more direct evidence for it, would be amazingly important. I think that I would love to see some evidence in that direction.
John?
Well, I think one has to look in a bunch of different directions. And Cumrun referred to dark energy and dark matter, and these were both arose from astronomical measurements. And so there is this rather marvelous model that we have that couples the structure of the universe very early on, and as we see it now, to fundamental particle physics. And so that's kind of the ultimate accelerator, if you like. And so that's one direction, is to actually use observational astronomy to try to get at some of these things. Neutrino physics, as Cumrun said, is giving us some interesting insights. There are rare decays that can give us a window into new physics at very high energy scales. And then there's kind of the direct brute force approach of colliding protons together. Now, one interesting scenario is this electron-positron linear collider, which is expensive, but it actually could give us an interesting window. And this is one of the things that people are sort of looking for, what we may find at the LHC and then what you might build on to further explore it. So there are all these different directions where one has to sort of probe simultaneously, but the fact that all of these parameters kind of, I don't know, talk to each other, all these observations talk to each other, cosmological implications are affected by particle physics and vice versa, you have to paint a coherent picture. So we're actually getting all this from a lot of different areas. So you have to sort of pick one and work away at it, and then, kind of take the next thing. And technology is very important because technology gives you a window, and so you can be very surprised with what somebody might come up with, let's say in accelerator technology or something like that, or an idea that can give you a new window into new physics too. So all of the above.
Young man in dark sweater there.
This is more of a general question, but my understanding of theories is that they have sort of a stacking property, that you have some basic theories and then you build on them. So when you have a theory that's sort of high up and it doesn't work out and it doesn't prove itself, how far down the stack do you go to see what the problem is? Is it something that is a fundamental anomaly that is manifested at a higher level, or is it just something wrong with the latest or the highest version of the theory? I'm not sure if my question makes sense. So if for example, the Higgs boson experiments didn't work, how far down the theories would you go to try and figure out where you might make a change?
Well, I'm not exactly sure I understood exactly the question, but so it depends exactly what you mean by how far down you go, how far up you go. But if Higgs wasn't discovered, I already said there were other models we were looking at, so there would be no problem. Say, okay, good, this model is wrong, let's get the other model. So there's no shortage of models. Our problem has been to narrow it down rather than to rule out one particular one. We have huge number of possibilities, so try to find which one is realized in nature has been the question. The idea of which theory is wrong or false and so on, by now we know so much about quantum field theory and how it works that we don't have a logical misunderstanding about quantum theory. That theory is well established, we understand this, and we understand a whole possible would-be quantum field theories which are not realized in nature. But we have studied them just for the fun of it, just to get understanding about how quantum field theories work. So we have a huge amount of machinery and understanding of it. And in fact, one of the beautiful textbooks on that subject was written by Matt on this. And so we know a huge amount. It's a classical subject by now. So it's not like we throw out the theory, but if it doesn't pan out, then we look at tens of thousands of other theories that might be available in terms of matching. So it's not like we are short on theories, on models, I mean.
We have time for 2 more questions. Up there, lady with long hair.
Thank you. So earlier a comment was made that made me kind of feel comfortable. I understand the standard model and quantum mechanics about as well as any non-physicist might, but I don't know much or anything about pop culture or God. And I'm very curious I've always been curious how the Higgs boson acquired the name, the God particle, in newspapers and media. I don't understand much about religion, so
Who wants to tackle this one?
I think it was Leon Letterman was writing a book, and this is like one of these problems with how publicists come up with it. I think as it was related to me, and this is like third hand, so God knows if it's really correct. But they wanted something jazzy about what Leon was writing, and I think he just threw out some titles, and the God particle was one of them, and for some reason the publicist ran with it, and I can tell you from my own experience, sometimes the presses actually come up with the title and saddle you with it. So I think that's what happened.
I thought Leon called it the goddamn particle, and then they
That-
just
that was-
shortened it.
recently, yeah,
Sorry,
recently.
sorry. I was just quoting.
And I should add, all physicists hate that name for the particle.
One more. Okay.
Have to split the symmetry.
The person in the middle. Young person in the middle. Can you pass the microphone?
So you were speaking about some of the new insights that we should expect as undergraduates. I'm an undergraduate. Are there places that you think those will happen? Big labs like CERN or places like this? That's it.
Place meaning geographical place?
Insights into what?
Like labs. Like are there labs where you see
Experimental discoveries. Where do we expect them to be?
Yeah.
So, so a couple of things. You could be in a mine shaft, dark matter. We could find it there if we're going to find it. I'm not actually being funny. Really deep down. We could also find new forces at the collider, at CERN, which would go the wrong way from where Cumrun wants to go. Instead of making the forces one, we would make more and more forces. Like if we found quarks were composite particles, for instance, or electrons were composite. So it could happen there. And it could happen on a satellite. So it's hard to know.
How about
Maybe
that?
even a balloon.
How about Antarctica?
And it could happen at the South Pole.
Top of the mountain.
Where's the top of the mountain?
Chile.
Yeah.
Oh yeah, could happen in Chile.
Most exotic places on Earth is where they will.
It's kind of cool. You could go to a lot of places. That's one thing, just for any undergraduates who are thinking about particle physics. It's probably, don't tell anybody, but it's probably the coolest travel career in terms of physics. Because even though people love having their own little experiment on a table, you never have to go anywhere. Yeah.
You don't like Jefferson?
Well, I mean, I don't, did that answer?
Yep, that was perfect.
Okay, so I would like to wrap up by asking the panel, just, you know, if you wish, if you hope and just to get your wish, what kind of discoveries you hope to find in, I don't know, next 10 years, 20 years?
Something nobody.
Something you personally want to find. Please, John.
Something nobody expected would be the best thing, because that would force everybody to rethink what's going on, or something that all of a sudden an aha comes and things fall into a place that you weren't expecting, which I know that sounds rather vague, but I personally think that the idea of vacuum energy at this energy scale is extremely weird, and so I wish I could get some more insight into what the heck the Higgs mechanism actually is from the perspective of these artifacts that are in the theory, but we don't know what they mean. So I guess that would be my biggest hope.
Well,
Cumrun.
Of course, I'll be most excited if some of the predictions we have made in my work with my student pan out in any way. And in that in particular implies we were assuming supersymmetry might be discovered at Large Hadron Collider, so hopefully we still have a chance if that is happening. And in particular, a shadow particle of tau particle, which is called STAU, having a lifetime of about an hour or so is what we are predicting. So that I would love to see. I would love to see that. But besides that, I would say that any discovery which has to do with new things, I mean, we are not that picky. If it's supersymmetry, great. But if it's not something other than what has been predicted for the past 50 years, a priori, that's something that's new, that would be extremely interesting, because it will actually guide the next round of physics thoughts that we need to have. And if it connects with dark matter, which is one of the big mysteries, that would be fantastic too, because it will solve two things at once. So,
Matt?
Yeah, I mean, I think I agree with both of my panelists that, I mean, anything would be exciting. I like to, what I expect is it'll be something that we haven't thought of. And I'd like to imagine, so in the late 90s, people started coming up with models with extra dimensions of space. And what these extra dimensions of space would show up to a first approximation at a collider is particles like all the ones we have, but heavier. So kind of mirror copies of the standard model with masses that are very evenly spaced. So they're resonances with, you know, you would have the W boson, and then you have a W boson, you know, one TeV heavier, and then a W boson TeV heavier than that, and then a TeV heavier than that, and so on, and kind of a stack all the way up. Now, you can imagine, so before the LHC, there was another machine called the SSC, which never got built. It was almost built. They built a tunnel, and then they ran out of money, or they got canceled. But this might have turned on in like 1993, which is maybe 5 years before these extra-dimensional models came on. Now imagine they turned this on, and they started finding these particles, and they found a particle like the W boson that was a TeV heavier, and then another particle a TeV heavier than that, and then another particle a TeV heavier than that. And then they would say, oh my God, there's this pattern. We see this evenly spaced spectrum, and then we could take a Fourier transform, and it looks like an extra dimension, and hey, look, there's extra dimensions of space. And that could have happened before the theorists came up with the idea, or after. Now, it turned out that probably, well, neither happened. The theory wasn't right, and the experiment didn't happen. But, you know, we're only so good at thinking of stuff. And you know, there's a few ideas we've come up with, but there's a lot more that we haven't. And why we should think of the thing before we build the machine rather than after doesn't make any sense to me. It seems much more likely that we'd build the machine and see the stuff and then figure it out. And that's certainly historically how particle physics has developed. So I don't see any reason that won't continue at the LHC, that we'll find something and then we'll sort it out. And then afterwards it'll make a lot of sense, or not. But that's why I really think that you know, we can see something and it can be very exciting. And if we do, it's probably unlikely to be one of these ideas that we got just by thinking. But you never know.
I think Matt is becoming an experimentalist. I think that
That's kind of true.
I was listening, was thinking, are you kidding? Like, yeah, of course, we're taking over.
That's your counterexample?
The bad pigs take over. I have always wanted in my career to discover something that the discovery was so exciting that I actually peed in my pants. And it hasn't happened. And I have to say that it's getting easier and easier. But here's what I'm thinking. We discover, in one discovery, we have some interaction in which supersymmetric dark matter comes, recoiling off a graviton, and possibly something from an extra dimension. That would definitely do it for me. And I'm looking forward to doing that first. But unfortunately, the theorists are so fast that they've thought of everything, almost everything. But if there's any young theory-type people in the audience, we need some more ideas. These guys are getting old.
Thank you. And so, just in case you didn't have enough of Melissa Franklin, there will be a lecture next week, exactly same place, same time. I had this impression that the title was Melissa Franklin Talks Higgs, but apparently it's a little longer than that. Please come, and there will be fresh jokes, I hope. So let's thank the panel member, and let's also thank the graduate students, Stephen Chan and Julia Gonski. Thank you very much for coming.